encoded in the fact that you're integrating something and those like local temperatures and all that are like integration. But if you write it in terms of the C++ form, it's very clean. Okay, so yeah, so this is what the anomaly polynomial looks like in general. There's a piece involving only the gauge field that has to cancel, that restricts the mattering content. There's a piece that involves only the global symmetries and gravity, and these are the 't Hooft anomalies. Then there's some other mixed terms. This is these mixed terms I mentioned here, mixed terms involving one global symmetry and two gauge symmetries. We can also consider the case, for instance, where we have one gauge symmetry and two global symmetries. And that's something which was the subject of a recent paper that I wrote with Cordova Dimitrescu, so I won't discuss it today, but these mixed anomalies are not actually anomalies. There's a story that's kind of a long story that we discussed in our paper, recent paper, which was a long paper. But yeah, because of no time, I won't discuss it. Another example that I won't really discuss because of lack of time is the small SO32 instanton example. Here I mentioned before, like the small E8 instanton example. If we look at, there's an analog of that for the small SO32 instanton, which was written down in a paper by Witten in 1995. That theory has a global SO32 symmetry, just like this theory that I wrote down before, and a global E8 symmetry. And it has some matter content. And if you anomaly polynomial, you put it 0 when all of the measurements are turned off. So this is a theory which is anomaly free. So this theory exists in dimensions and it's anomaly free. You don't need anything like a Green-Schwarz Westinghouse mechanism to cancel its anomalies. Now the flip side of it being anomaly free is that it's a boring theory in the infrared. This theory is just some infrared free theory, which is like 1-1 theories, which can't be made super conformal. But the string version of this, by the way, is T-equal to the E8 belt string. Yeah. So the question was if the anomaly polynomial is unique. There's it's a property of the theory, and so there's a way in a given theory, in principle, it's something that we can calculate in the theory. So if the theory is a free theory, the way to calculate it is to look at a paper by Albert Gomez and Witten, where they wrote down what the anomaly polynomial is for every free theory in every dimension. And so by looking at that paper, we can write down the anomaly polynomial. If it's not a free theory, then we have to work harder to write the anomaly polynomial. In fact, I think on the next slide I could count some anomaly polynomials for these interacting theories. But yeah, in principle, there's a unique way to do it. I see my time is basically, do I have like a few minutes or is it up? Okay, I have a few minutes. Okay, so maybe since I've basically run out of time, I'll just flash some slides, since I have slides now anyway. So one nice thing about supersymmetry in lower dimensions is that you can relate the conformal anomaly A to the 't Hooft anomalies. And so we could try to do that also in 6 dimensions. So in 6 dimensions, the anomaly, in 6 dimensions, this ID plus 2 becomes I8. And so instead of having triangle diagrams, we have square diagrams in 6 dimensions. So we have square diagrams with gauge fields at the edges of the square. So this is in 4D and 6D. And so that's what this box represents. It's an anomaly diagram that we can compute. And so this is something that can be computed, and it has anomaly matching. And then using a variance of a calculation that was done by Harvey, Manassian, and Moore, where they computed for the 2-0 theory of type AN, they computed that the anomaly wasn't just n cubed. Some coefficient in the anomaly piece wasn't just n cubed, but it was n cubed minus n. And they got the minus n by using M theory and some argument with anomaly inflow. So given the time, I planned actually to, I have notes where I think, by the way, I'll make these notes somehow available, but I have notes where I was planning to go through some of this, but I'm just now like rushing because of lack of time. Yeah, so these are all exact information about this theory. So the nice thing about 't Hooft anomalies is that you can also often compute them exactly by some tricks, like anomaly inflow. So the fact that this has like all of these subleading in large N things is some interesting information about these theories. And there's a way so this thing in the box is a result that we obtained with in a paper with Cordova and Dimitrescu a couple of years ago, where we related the conformal anomaly A to these alpha, beta, gamma coefficients of the 't Hooft anomalies. And a key thing that allowed us to do this was a nice paper written by a group here at Trieste. I mean, if you look at the authors of this paper, it came from Trieste. It was by Bergschaft, Salam, and Sezgin in '86. And they were looking at some 6-dimensional supergravity with some R² terms. And so they supersymmetrized the R² terms. And that's exactly what we needed in order, like we were able to look at their results in the supersymmetrization of the R² terms and infer how to relate the conformal anomaly A to these 't Hooft anomalies. So this is some general result that if you know the 't Hooft anomalies, you can plug it into this formula to get the conformal anomaly A. Like for the n small e instantons, this is the conformal anomaly A, and this is an exact result because the anomalies were exactly computed by this group, and then this is an exact formula following from supersymmetry, and so you get these things. And I think for lack